In this lesson, we'll start learning about quadratic functions, which model real-life situations where direction of change reverses its course in the middle. For example, height against time. When a ball is thrown in the air, height first increases, but when the ball reaches at its maximum height, then it starts decreasing, while its time still continues to increase. A polynomial function of second degree of the form f of x equal to ax square plus bx plus c, where a, b, and c are constants, but a is not equal to 0, is called a quadratic function. We'll consider the simplest form of the quadratic function in which a is equal to 1, b, and c are both equal to 0. So let's get started with the graph of function y is equal to x square. Graph of function y is equal to x square. In order to draw the graph, first we have to find the table of values. So step 1, we'll find table of values for which we have x, and for x we assume the first value is minus 3, then minus 2, then minus 1, 0, 1, 2, and 3. These are possible values, and against each value of x now we will find the value of y. So for y, here we have minus 3 square because y is equal to x square. So this will be equal to 9. Here we have minus 2 square, which is equal to 4, minus 1 square, which is equal to 1, 0 square is equal to 0, 1 square is equal to 1, 2 square is equal to 4, and 3 square is equal to 9. So the pair of values which we need to plot would be like this. xy would be minus 3, 9, and minus 2, 4, minus 1, 1, and 0, 0, 1, 1, 2, 4, 2, 4, and 3, 9. Now let's plot these points on a graph paper. On the grid here, let's take this horizontal axis as x-axis, and for positive values we have x, for negative values in the left we have x dash, for positive y values we have y, and for negative y values let's label this side as y dash. The first point that we need to plot is minus 3, 9. So we go minus 3 toward left, minus 1, minus 2, minus 3, and then 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's where we end up for the point minus 3, 9. And the next point we plot is minus 2, 4. So again, 2 units toward left, minus 2, and then 4, 1, 2, 3, 4. That would be right here. Label this as minus 2, 4. And then is the point minus 1, 1. So let's label this as minus 1, 1. And 0, 0 is another point on the origin. 1, 1, and 2, 4. 1, 2, 3, 4. So this will be the point 2, 4. And the last point that we are going to plot is 3, 9. So 3, 9 will be right here. So this is the point 3, 9. If we estimate a smooth curve through these points, the curve will look like this. This may not be the best graph that you have seen, but at least it will show you a trend. So here we get to the origin, and on the left side we also start from this and go through these points. So this is the graph of the function y equal to x square. This graph does have some very interesting properties. In fact, every quadratic function has a graph which is parabolic in nature and has all the properties of parabola. Now, because this graph is parabola, so there must be a point here somewhere which we can label as F and call it focus point. Now, this point focus, which is called focus, has very interesting property. If we have this as origin, then we estimate a straight line below x-axis. This is just an approximation. So this line is called directrix. Let's call this as directrix. And height of F above the origin is exactly same as the distance of this line below the origin. So if there was a point T here, then OF and OT must be same. So property 1 is F is called focus of the parabola, because this graph is a parabola. And the property of F is that if you take any point on parabola, let's take this point -1, 1. So this was the point. Then the distance, and call this point as, let's call it as P. Then the distance of P from F will be denoted by PF, and the vertical distance of P from this line, which we called directrix, is exactly same by the definition of parabola. That's how we, so if we call this as M, this point on directrix, then PF and PM are exactly same. If M is a point on directrix, then such that PF is same as PM, then F is called the focus of the parabola. Then F is called focus of the parabola. And consequently, this is the point on the graph of y is equal to x square. So if this is the line, the fixed straight line below the graph of parabola, or y is equal to x square, so let's call this fixed straight line below the graph, below the graph of y is equal to x square, such that every point on the parabola, every point on parabola is equidistant from F and the line. Then that fixed straight line is called directrix. Then fixed straight line is called directrix. And the point O where the graph changes its course is called vertex. So number 3, the point O here, the point O 0 0 where graph changes its course is called vertex. So every graph, doesn't matter y is equal to x squared or y is equal to minus x squared, will have a point where graph is going to change its course or its direction. So that point could be the highest point on the graph or it could be the lowest point on the graph, is called the vertex. So the point O 0 0 where the graph changes its course is called vertex. It is either the highest point or, and it will be highest point if the equation was y is equal to minus x squared, or lowest point if the equation was y is equal to x squared, is called vertex. So now the line passing through the vertex and the focus is called axis of parabola. So this is number 4. Line passing through F, the focus F, and vertex is called axis of parabola, and the graph is always symmetric about this line, and the graph of y is equal to x squared is symmetric about this line. So here we have discussed some properties. We have discussed vertex, we have discussed focus, and we have discussed the line of symmetry, axis of symmetry, or axis of parabola. The length between F and the vertex is called focal length. So let's write that down as well. Number 5, distance between focus F and vertex V, which in this case is 0 0, is called focal length. So these are few properties. And line segment, let's do another one, which is called lattice rectum. Line joining two points of parabola, passing through focus, and perpendicular to axis of parabola, and perpendicular to axis of parabola, is called lattice rectum. So that is, let's name this as lattice rectum. So here, if we take a look on the graph here, this line here is lattice rectum. So this line AB will be lattice rectum. Let's name this as A, this as B. Because it's as high as is the focus above the x-axis, so its equation can be found as well. But we leave those kind of things for later. And now we will discuss how do we find the intercepts. So for parabola, for any parabola, for any quadratic function, we can find intercepts. We can find intercepts like this. For x-intercept, we will put y is equal to 0. For x-intercept, put y is equal to 0 and get values for x and solve for x, which gives x-intercepts. In this case, in y is equal to x square, graph of this quadratic function doesn't intersect x-axis except origin. So in y is equal to x square, 0, 0 is the only x-intercept, is the only x-intercept. And for y-intercept, obviously we are going to put x equal to 0 for B part. For y-intercept, put y equal to 0 and get values for x and get values for x. This gives you y-intercept. So these are few properties for the graph of quadratic function y is equal to x square, or for that purpose we will modify and we'll write many more different quadratic functions. But basically what we will be interested in is finding and discussing these properties for the graph of any quadratic function. See you in the next lesson.